Okay, so this lecture we are going to focus on contact stresses. Contact stresses. Okay, so let me plot one diagram. Okay. This is a rough diagram, not complete one. Not perfect, but okay. This is of diameter D2 and this is of diameter D1 and suppose this is the x-axis and this is going towards y-axis and it's subjected to a load F F so as we said that the typical situation is two bodies in reciprocal contact with a normal load applied to the contact surface, which is schematized in this diagram. Normal load F is pressed and transmitted to the contact area. So in order to analyze this problem, we can follow two different approaches. First one is Hertzian contact stresses, which are related to macroscopic contact geometry. Macroscopic contact geometry. The other approach is stresses associated with microscopic asperity contacts. So first one is related to this first one is related to the Hertzian contact stress, which is a theory developed by the Hertz about the elastic stress field in this contact area. So this analysis is just an elastic stress problem and it is performed by assuming an ideal geometry of these bodies in a particular very smooth surface in the contact area. So in particular, Hertz stress is related to the static loading on these bodies. So you might have a question that what is meant by a smooth surface. So if we look more precisely on this contact area, of course we mentioned we have an intrinsic roughness of both objects. So when they are in contact, the real contact area is given by asperities because we have not a flat profile but some asperities somewhere. So when these asperities come in contact, we have a real stress transmission, and then originally the contact area is very small. But in geometry, like in this figure, we have high local pressure. So these small asperities are easily flattened to generate a real smooth surface. So this geometry is named as non-conforming contact. So a non-conforming contact means the curvature of two bodies are different. So in non-conformal coating, the contact area is relatively small, and then local stress is very high. The local average pressure is large. Now, if we have very stiff bodies, the contact area is small. So what is the general conclusion of all this analysis? So let's plot a simple graph. So x-axis represents distance from contact surface. And y-axis represents ratio of stresses to maximum load. Ratio of stresses to maximum load, that is Pmax. Now let's plot the graph. So in this plot, we are going to analyze the normal stress component in the vertical direction, that is z direction, and in horizontal direction, that is x and y direction. So this component decreases as we move in depth from the contact region in one or the other body. So this is sigma z curve. This is sigma x and sigma y curve, and this is tau max curve. So this one is tau max curve. So we have continuously decreasing stress. The highest stress is found in just in the contact area, but if we look at the shear component, the trend is different, and we attain a maximum value at a given depth below the contact area. This depth is around 0.5 a, that is half the radius of the contact region, that is the half the radius of contact region. We know that in ductile material, the plastic deformation is triggered by shear stress. So this means that in this condition, we can produce subsurface cracks during the tau max. Subsurface cracking is the most common failure mode of this type of contact. So is there any good effect of coating that we can apply on these bodies in this condition? The answer is unfortunately no. Our coating can improve the wear resistance and can modify the friction behavior of our bodies, but it is not able to counteract this failure mechanism because the depth is too large. Now if we calculate roughly the depth of the maximum shear stress in a typical contact ball bearings of diameter 10 mm rolling on a cylindrical path. So if we apply a discussed analysis knowing the elastic moduli of these materials, the applied load F and the radius of the sphere, we estimate the position of tau max roughly to which lies between 0.1 to 0.3 mm below the contact surface. So this maximum shear stress is well inside our body. So any coating with few micrometer in thickness is not able to counteract this effect. So still we have a risk of subsurface cracking. The situation is different if we consider conformal contacts. For example, as we said, a piston moving inside a cylinder. Surfaces with same location of the center of curvature and same curvature compared to the sliding surfaces or two flat surfaces sliding on one over the other one. So if in this condition we apply a normal load, we have a typically much larger contact area, and then average stress is much lower. So typically contact is through asperities. We should remember that Hertzian analysis holds in elastic range. So if we extend this concept to a contact between two asperities, we are speaking of the bodies in range of some micrometer. So this depth is proportional to the size of the object, so it is very close to the contact area. So typically inside our coating, so in this case, applied coating can modify the stress distribution, thereby increasing the resistance of our surface materials. So we can remember this general conclusion to define the strategies to increase the load carrying capacity, which we are going to discuss in the next lecture.